Hello everyone. We now know that, after the last lab, that this turning effect, this thing that causes rotation, is now something we will call torque, right? Which is a lever arm times a force. It depends both on how much force is applied and where that force is applied. So let's start looking at some more complex situations. Here we have an example of, we have a meter stick. Okay, happens to have this very strange mass, which just makes the numbers work out well, of 0.306 kilograms. It's pivoted at one end, so there's a pivot right here. We could call that a fulcrum, if you wish. Right? So it's on a little knife edge there. And it's held horizontally by a vertical string. So there's a string at the far end holding it up, and it's being held horizontal, right? And it can pivot over here. So first thing I want to do is to draw a force diagram, of course, except drawing our old force diagrams aren't going to do us any good here. Our old force diagrams, we considered all parts of the object as if they were moving the same. Right? We consider the cart as being just one big object moving down the track. Now, we have to be concerned with not just what forces act and how big those forces are, but also where they act. And so we need to draw what we're going to call an extended force diagram. We're going to draw these forces where they actually act on the object. So we're not going to draw dots anymore and draw all the forces radiating out from the dots. We're going to draw the object and draw all the forces acting there. That's so that we can see a little bit better the torques. Okay, so this is going to be a new thing, a little more complex of a force diagram idea. So, what forces act? Well, of course, first force we always put on a force diagram. There's gravity acting on this meter stick. But then that begs the question, okay, if gravity is acting on the meter stick, where does it act? Well, obviously, gravity acts on all the little parts, right? There's a gravity that acts on this little part, these little parts. There's a gravity that acts on this part. So where are we going to draw that force of gravity? What do you think would be a good place to draw that force of gravity? If you think about what we did at the beginning of the impulse and momentum unit, right, and hopefully some of you are saying, yeah, let's draw it maybe at the center of mass. Because remember, the center of mass was where we could think of all of the mass of an object as acting, was the pivot point, if you will, right? Well, on a meter stick, right, that's going to be in the center of it. But we're not really talking about mass here, we're talking about gravity. So we do have a new concept, very related to center of mass, called center of gravity. This is the single point where you can think of all of gravity as acting. Now, unless you're in some pretty strange region of space, the center of mass and the center of gravity are going to actually be the exact same point on a body. Okay, the only way they could be different is if the local gravitational field strength wasn't a constant. And for that to happen on Earth would be pretty bizarre. Okay? I mean, even if you have a very sensitive measuring device, if you measure the gravitational field strength at ground level, then go up into a really tall building and measure the gravitational field strength on the roof, you're not going to notice any difference, except maybe many, many decimal places out. Right? You have to be very sensitive, because we're not really that far away. We haven't really changed where we are with respect to the center of the Earth. That's something that we'll get into in a unit on universal gravitation at the end of the year. But unless, again, you're somewhere where the gravitational field strength at one end of the meter stick is different than at the other end, okay, the center of mass and the center of gravity are essentially going to be the same point. You can imagine, and I'm not going to do it, but you can imagine doing the calculus, right, and gathering up all of those forces of gravity as if they acted at the center. So for us, we're going to draw the force of gravity right from the center of the meter stick. Okay, center of mass, center of gravity, same place. And so there we have our force of gravity acting from the center of gravity. What other forces act? Well, the meter stick is being supported at the fulcrum here, at the pivot point, right, by this little triangle deal here. So if it's a support force, that would be a normal force. That normal force would act at the point of interaction, where the fulcrum and the meter stick touch. And so notice I started it at the bottom of the object here, and it goes straight up. There was also a string hanging from this end, or actually pulling from that end, right? So that string, which is a force of tension, would also act up. Do you see the difference between this force diagram and our old school force diagrams, which would have just been a dot? Right? Now we can see where those forces act. So it's important now that we transition to these extended force diagrams. And those are the only forces that act. But even though they're forces that act, are they torques that act? Does each one exert a torque when it can pivot over here? Well, gravity does. Right? I mean, if you weren't holding on to the string, right, gravity would make it rotate this way. Make it rotate, what is that, clockwise. Right? Tension does, because if you pulled harder, right, you could make it rotate counterclockwise. But what about the normal force? In the last lab, did any of you hang masses from the very center hook? The one that was right underneath the axis of rotation? And if you did it have any turning effect? Really didn't, did it? And it didn't make it rotate. Consider pulling, instead of pushing perpendicular to a door, consider pulling straight out through the hinges through the door. See what I'm saying? So instead of pushing perpendicular to the door frame, perpendicular to the hinges, what if you pulled along the door? You going to get any rotation? You going to get any torque? No. You pull as hard as you want, unless you pull it off the hinges, you're not going to get any torque that way. Right? So forces that act through the axis of rotation exert no torque. They act, as it's called, radially. You'll hear me say that terminology. So a force that acts radially exerts no torque, right, through the axis of rotation. Again, pulling straight out on a door is probably the best example I can usually think of, but I like that lab gave you a little hook in the center, right, and it doesn't actually provide any turning effect. So in this case, the normal force, which is a force and it's there, provides no torque, but gravity and the tension do. The next thing I want to do is we're going to be figuring out what all these forces are and all that kind of thing. I'm going to give you a scaffolding device here, a little modeling technique, and we're only going to use this for a couple of days and a couple of worksheets. But it's basically a torque bar graph. Okay? We're going to list out all of the possible torques in this area, positive or negative. Positive, remember, means counterclockwise. Negative means clockwise. And then over here, we're going to list out the positive or negative net torque. And so we're just going to keep track of everything. Okay? Like an LOL diagram or a momentum diagram, right? Bar chart. Now, this is really just an organizational tool. Like I said, couple of days, and then we'll get to just writing pure equations. But I just kind of want to gather up your thoughts here for a few days. So, let's go through the forces and therefore the torques and list them out, and the net torque, and list them out here and see what we can find, right? So first off, let's just go from left to right. We've got the normal force, but as we talked about, it exerts no torque because it's acting radially. It's acting through the axis of rotation. Okay. Next one we're going to do is the torque due to gravity. Well, the torque due to gravity is a clockwise torque. Right? And since it's a clockwise torque, because it would make it rotate clockwise, right? That makes it negative. Now, we don't know exactly how much. We'll calculate that in a moment. But kind of like we did with LOL diagrams, I'm just going to call that 4 blocks of torque. A negative 4 blocks of torque. And then let's calculate it. Torque is lever arm times the force of gravity. We weren't given the force of gravity, the weight of the meter stick. We were given its mass, and we sure know how to convert. Right? F of g is mg. So now we just have to plug the numbers in. Right? Well, one little thing, what is the lever arm? The lever arm here is the distance from the axis of rotation, the pivot point, to the point of application of the force, which in this case is the center of gravity. The center of gravity in a meter stick would be where? right in the center, which is how far from the edge? Half a meter. With me there? So our lever arm for the force of gravity is a half a meter. Our mass is 0.306 kilograms. And assuming we are on Earth, our gravitational field strength is our old friend 9.8 newtons per kilogram. Note the kilograms cancel, and we're left with Newton meters of torque. And because I picked a very special number for the mass, we end up with a very nice round 1.5 Newton meters. Now that's the magnitude of the torque, right? The actual torque is a negative 1.5 Newton meters. See how I put that now on our bar graph down here? Bottom left-hand corner, folks. It's a negative 1.5 Newton meters. Right, so this allows us to calculate the magnitude, and then we have to throw on the direction. We have to decide, is it counterclockwise or clockwise? Is it positive or is it negative? So there's the torque due to gravity. Now what about the torque due to the tension? Well, we can't just calculate it right now, because while we can figure out the lever arm for the force of tension, we don't know how big the force of tension is. But perhaps we can get it from context. So let's go to the net torque. What's the net torque acting on this thing? Well, notice it's not moving. Right? Since it's not moving, it's got a constant velocity. Since it's got a constant velocity, and it sure looks like the lab, right? The torques must be balanced. And if the torques are balanced, that means that the net torque, this is tau here, right? So our net torque has to be 0. Just look like something we've seen before? Yeah, it looks like Newton's first law, right? Oops, come back here, you. So this is like Newton's first law here, right? The torques are balanced, so that means the net torque is 0 because the angular velocity doesn't change. Well, if the net torque is 0, then that means the torque due to the tension has to balance out the torque due to gravity. And if there were 4 boxes, or negative 1.5 Newton meters of torque due to gravity, then there's got to be 4 boxes but positive, or positive 1.5 Newton meters of torque due to the tension. You might be able to see the equation we would write out here, much as we do in cases of balanced forces. But we'll get there. And this is, again, like I said, an example of Newton's first law, but for rotation as opposed to linear motion. When the net torque is 0, the object continues in its same state of rotation. Ooh, there we go. So let's now find how big that tension in the string is. We know that it's 1.5 Newton meters. We also know that it's the lever arm times the force of tension. Right? So if we solve, but what's the lever arm for the force of tension? Well, it's on this end of the meter stick, and the pivot point's over here, right, on the other end. And the lever arm is the perpendicular distance from the axis of rotation to the point of application of the force, which of course would just be 1 meter. So we divide, and we get 1.5 newtons for the force of tension. Oh, isn't that nice? Right, so we've now calculated the force of tension. Now, this case that we're looking at is something special. Okay? It's got a special name to it. This case where the net forces and the net torques are 0 is something called equilibrium. Right? We talked about this a little bit in terms of forces, but now we can also add in torques. Right? So true equilibrium is when both the net force and the net torque are 0. Everything is balanced. Okay? And this is, in fact, an even more specific case of equilibrium because our object is not moving. It's neither moving linearly nor rotationally. Okay? We can still be in equilibrium, right? We can still have a net force and move. We just have to move constantly. We can still have, 0 net force and move. We just have to do it constantly. We can still have a 0 net torque and rotate. We just have to rotate constantly. Right? But in this case, it's not moving or rotating. Right? So we call this static equilibrium. Okay? Static means not moving, if you remember its use in static friction. It was friction when the surfaces aren't moving with respect to one another. So this is static equilibrium. It's a very important case. Okay? If you go into engineering, mechanical-ish engineering, you're going to take like a whole semester class, which I usually call stats, which is all about static equilibrium, how to put things in static equilibrium, and then you might get into like materials and strengths and strains and things like that on materials and whether your materials can handle a particular static equilibrium. If you think about building things, right, being able to put it into static, for example, an architect, you better be able to put things properly into static equilibrium or your buildings are going to fall. Right? So it's a very important special case. And again, it occurs when the net force and the net torque are zero and you don't have any motion. So the linear velocity and the angular velocity are all zero. Remember our use of omega for the angular velocity. Okay, so we're going to do this for a few days here, and really up until the first quiz over the rotation unit. Right? Kind of like we did balanced forces. Right? We're going to do balanced torques, right, up until we take a quiz here. So we're just going to get into more and more and more complex situations of static equilibrium. So since the forces are also balanced, we can write a force equation, a Newton's first law force equation. We have two upward forces, and they balance out the one downward force of gravity. You might have noticed that when I drew them, right? So I can draw a torque equation, but I can also write out a force equation. And if I solve it, we know that the normal force is just equal to the force of gravity minus the force of tension. And since we know both of these, right, we can figure out how big the normal force is. Force of gravity is, of course, mg. Force of tension we found in the last part as 1.5 newtons. By the way, if you multiply this out to at least a couple of sig figs, it's 3.0 newtons. So we have 3.0 newtons of gravity. It weighs 3.0 newtons minus 1.5 newtons of tension means the normal force also happens to be 1.5 newtons. Now, there's no magic here. Okay, it's not always, oh, look, this is half and that's half. It worked out that way because of the geometry of the situation, because of where these forces were applied, right? And that's why we have to deal with extended force diagrams so we can see this. If we hadn't looked at torques, we never would have been able to figure out this equation because we wouldn't have been able to determine the force of tension. And so knowing torques, drawing extended force diagrams, gives us more to look at in a particular problem. Right? More things that we can calculate, more things that we can predict about a situation. And again, this is a very special situation called static equilibrium. And so for the next few days, up until the next quiz, we're going to be looking at more and more complex static equilibrium cases.